Hello and welcome to this next module about the Lighthouse project in AGARTALA. My name is Sabine Giegelmeier and I'm Business Development Manager at the Fraunhofer Institute for Building Physics IBP in Germany. The entire sixth module is about the Lighthouse project at AGARTALA, which uses the technology of prefabricated concrete modules that are assembled at the construction site. In the fifth part of this module, we review the basis of thermal comfort assessment. In particular, we will again discuss the so-called predicted mean votes, PMV. This evaluation model was originally developed by Ole Fanger and makes it possible to estimate how a certain room climate is evaluated by people. In this unit, we will also see how this evaluation method can be adapted to specific conditions. For example, to predict comfort in buildings where air conditioning is not installed. In addition, I will show you some simulations where we will see what influence the different constructions have on the thermal comfort. But now let's start with the recap. It has always been difficult for building designers to plan a building in such a way that all people with their individual needs feel comfortable in it. Ole Fanger had therefore developed a model that can be used to quantify people's individual requirements. They thus become measurable and comparable. This data can then be used for the planning of comfortable buildings. He has calculated an index that represents a thermal sensitivity state from a combination of physiological and physical variables. He has invented the so-called predicted mean vote, PMV. Thermal sensitivity is quantified using a 7-point scale representing the expected average rating of the indoor environment. The calculation of the PMV, according to Fanger, takes into account various factors that affect people, such as metabolic rate, clothing insulation, air temperature, air velocity, mean radiant temperature, and relative humidity. This index was developed for static conditions, but can also be used when there are slight changes in the influencing variables. Then you have to use the time-weighted mean variables of the changing parameters for the calculation. From the PMV, in turn, the PPD can be determined, which stands for predicted percentage of dissatisfied. That means the percentage of how many people feel uncomfortable at a certain PMV. If the PMV model is used for building planning, limits must be defined for it. That means a range of the PMV that is still acceptable or not. Generally, a value of -1 to 1 is seen as the acceptable comfort range in building planning. This acceptance field allows for a range of dissatisfied people of 0 to 25%, whereby, according to Fanger, there will never be a case where 0% of the people are dissatisfied. So, for example, a room climate with a PMV of 1 says that it tends to be a little too warm, but still within the acceptable range. 75% of the people will perceive these conditions as satisfactory. 25% will not be satisfied. The classic PMV model is mainly used to assess the indoor climate of air-conditioned buildings. Investigations have shown that the calculation of the PMV was not entirely accurate for the buildings without active air conditioning. However, in order to quantify the indoor climate of naturally ventilated buildings in a similar way, no new calculation method was developed, but so-called PMV adjustment factors, also called expectancy factors, were introduced. To adjust the PMV to the conditions, it is multiplied by a given expectancy factor. The adjustment is based on the idea that people with lower expectations of the thermal comfort accept higher temperatures that one would expect according to the PMV model. In regions where air conditioning is commonly installed, expectations regarding the thermal comfort are usually high. This is also expressed in the expectancy factor of 0.9 to 1. If this is multiplied by the calculated PMV, the result hardly changes. In regions where air conditioning systems are not common, the expectation of comfort is also lower. This is evident from an expectation factor of 0.5 to 0.7. Of course, this has a great impact on the practical planning of the building. That means whether the planned buildings can provide a sufficient standard of indoor climate or whether it still has to be improved at high costs. But what does it look like when the adjustment factor is applied to the PMV? And how does it affect the resulting PPD, i.e. the number of people who are dissatisfied? We have already seen this diagram, but you can see here the influence of an adjustment factor of 0.5 on the PMV. Where all the other boundary conditions stay the same. This adjustment factor of 0.5 could be used in a region where there are few air-conditioned buildings and it is warm all year round, so it is sufficient for the buildings in AGARTALA. You can see the compression of the characteristic curve of the PMV. This means that many more people accept the thermal conditions and are therefore in the accepted range. The proportion of people who are not satisfied decreases sharply, because far fewer people have a PMV of 2 or 3. Now, after we have had a look at the theoretical background of the adjustment factor, let us have a look at the thermal comfort in AGARTALA using the adjustment factors for different building variants. We will look at the impact of a higher heat storage capacity of the materials used in the design and how this affects the PMV with and without adjustment factors. Various simulations were run to calculate the PMV and PPD values on which the adjustment factor of 0.5 is multiplied afterwards. But let us have a look at the results now. As mentioned, two variants have been simulated. The first one is the standard variant, as it is actually built. On the outside, a concrete filling of the lightweight construction is installed. The inside walls are filled with insulation. So overall, the inside has a low capacity. The calculation results can be seen as blue dots on this graph. We see that some hours are too cool, but the main hours are too hot. If we calculate the mean PMV, it is 1.00, indicating that it is a little too warm. Now we apply the adjustment factor. The main calculation points slide into the acceptable area, between 0.1 and 1, resulting in a PMV of exactly 0.5. We also see that the predicted perception is now very good, and only some complaints are in the range of too warm. Now we performed the same simulation but changed some construction materials. In this variant, we use insulation on the outer walls and concrete on the inner walls. We switch from low capacity to high capacity. The plot of the simulated PMV can be seen here in green dots. we see that there are fewer hours evaluated as too cool, but more as too warm. The calculated PMV therefore is 0.14 higher than in the variant before. If we now apply the adjustment factor to the PMV for AGARTALA again, the main calculation point slide into the acceptable area between -1 and 1, resulting in a PMV of 0.57. As before, we see that the proposed perception now is very good and only some complaints are in the area of too warm. In terms of thermal comfort, this variant with higher storage capacity performs minimally worse than the previous one with lower capacity. Let us wrap up the lecture. Basically, the PMV and the resulting PPD can be used to evaluate the thermal comfort in specific buildings. For different boundary conditions, one can make use of the adjustment factor to adapt the model. This re-evaluates the PMV and thus the PPD, so that a new planning basis for the building and the expected thermal acceptance is created. And with that, I would like to close this chapter and thank you for your attention. Bye and have a nice day.